The powerful Allison engine would drag the plane up before settling into the hover, and the blind descent was a nightmare. Another notable vertical attitude plane was the Bell X-13. The preliminary work on the problems of the feasibility of reaction controls for jet aircraft had begun in 1947, backed by the US Navy, with the same objective that had created the Pogo and Salmon, self-defending convoys. When the Navy ran out of funds, the Air Force's attention was already rising in relation to its own needs, and the X-13 Vertijets were to fill an Air Force order. The secret of the X-13 was that it hung on a hook and was designed to operate from a trailer. After a careful series of gradual steps ironing the problems out as they went, the team working on the project achieved what, on the face of it, seems an improbable aim: a portable plane complete with aerodrome. The system worked quite well, but after the initial fanfare of astonished applause when the plane first strutted its stuff, it seems to have immediately faded into an impenetrable obscurity. The two X-13s were among the most successful early jet Vtol aircraft, and the success and efficiency of their unlikely-sounding mission was perhaps as advanced as anything in the vertical field before the Harrier. They proved that vertical flight on jet thrust alone was both technically feasible and practical, and left little to question about the flexibility and usefulness of such an arrangement. But there would have been a way left to go to get it operational. The pilots still could not see, and there were loading limitations. Even without the weight of the retractable undercarriage, the thrust of the available engines left little reserve of power. The X-13 idea could have been refined, but it's highly unlikely now that it ever will be. Using jets to obtain sufficient thrust to go straight up required a lot more power from the engine than was readily available until quite recently. And the seemingly obvious solution to this was to have two sets of motors, with one set only involved in getting into the air. Hence, the Rolls-Royce flying bedstead, which was involved in trying to sort out the tricky business of developing controls for a plane that's rising on a pillar of jet thrust. The system developed on such vehicles operates very much in the same way as the lunar lander. The principle of control is reaction jets. It was still true that the accident that happened in hover was generally going to leave no time for recovery, but the work done with aircraft like these broke down a lot of the barriers standing in the way of vertical flight and made possible the use of far more conventional aeroplane shapes in Vtol rolls, though of course they themselves don't look like conventional aircraft at all. Where the Bell X-13 had quite practically hung itself up on a hook after a flight, there's been a lot of work on various systems for shortening the required landing length of aircraft, including another apparently fairly outrageous suggestion: to grab them with an arrestor hook and then slam them on their bellies on a rubber runway. Yet this too has been taken to the point where it actually works, and has been extensively tested. It was developed by the British, but the Martin Company showed a lot of interest in it as a companion system for their zero-length launch trucks, and the British showed the system off to several impressed American delegations. Despite the potential to miss the hook and sail back over the ship's side on occasion, the system worked after a fashion, and obviously cannot have been as silly as it sounds. Of course, crash barriers and arrestor wires have long been refined aboard carriers, and many planes have been fitted at one time or another to operate with these mechanical interventions. Apart from extreme examples like the rubber runway concept, the planes have clung to the weight penalty of their wheels, and most of the time, such landings are routine and go through without incident, though it does remain hazardous. If nothing else, the rubber runway serves to remind us of the lengths to which experimentation was pushed in trying to bring the demands of aircraft for takeoff and landing distance to heel. Vertical takeoff experimentation saw another variation in the Bell Model 65 with its swiveling jet engine. It had a relatively short career, and though it flew with the engine in both positions, it never did so on the same flight. No full transitions were made with the little plane. However, it settled several important basic issues and gave Bell the information it needed to proceed with its next, more ambitious design proposal. The Model 65 used engines off a missile, and when they burnt out after 4.5 hours use, that was the end of the project. One thing the Model 65 does well is show off its control jets. The nozzles can clearly be seen in the end of the wing, and the ducting along the side to take the compressed air to the rear cluster of nozzles is also evident. By constant and sometimes painful trial and error, the controls needed to hold a plane in relative obedience while hovering have been sorted out. The normal method of control with jet-engined Vtol planes is the use of air pumped to the plane's extremities, being vented as needed to hold position. In early wind tunnel tests with large working models of the system, 4 pilots sat at controls operating different bits. It was extremely complicated. Now, though not less complicated, it's a lot more automated. The Bell company has been absorbed in vertical flight research from the early 40s and has constructed an impressive range of prototypes exploring different approaches to the problems of getting a plane into the air without a huge runway. In 1956, they won a contract with the US Air Force to build a new plane, given the name X-14, to test their work on the concept of thrust vectoring and to serve as a test bed to sort out how to give pilots sensible controls for hovering flight, an area that was then still resolutely proving difficult. The X-14 was to be one of the most important aircraft in the long saga of vertical flight experimentation. In 1954 and 55, Bell had gone to the Air Force with a proposal for a VTOL lightweight day fighter and had managed to get the Air Force very interested in the proposal. As a step in exploring the technology that would be needed for such a plane, the Air Force had authorized the company to build a technology testbed aircraft. Bell's primary concern was to test the use of vectored thrust, which seemed to offer the simplest solution to the use of jet engines, allowing a plane that sat in a horizontal attitude. The test plane was built as fast as possible and as cheaply as possible, which coincidentally led to it being as small as possible. It incorporated existing engines and scavenged its parts from all sorts of aircraft spares. It had no canopy and no ejector seat. It was the minimum needed to do the job. The scheme of vectored thrust is to blow the hot engine exhaust through movable grills that aim them either at the ground or to the rear of the plane. On the face of it, a very simple approach. However, as is usual in these things, there are many complications. For example, if you point a powerful jet engine at something at close range, it is likely to do considerable damage. It will dig a pit in your lawn, or it will make your concrete bubble and smoke alarmingly. As a result, one of the things that the engineers working on the X-14 project had to turn their attention to was the constitution of concrete and how to build a heat and blast-resistant surface for the X-14 to test on. Here, if you'll pardon the expression, is the concrete embodiment of the X-plane series. Aviation's history is the chronology of a cascade of ideas, forming in the minds of individuals and being honed, expanded, or debunked. The generations of knowledge have succeeded one another at a bewildering speed, drawing constantly on what is proven to imagine what might be provable. It's been only when a hypothesis is put to the test that its full meaning has been discovered, both in the significance, success and implication of the idea, and also in the snags, complications, side effects, hazards and failure. On two levels, the X series enriched aviation by turning theory into hardware and then turning that hardware into practical machines. There are so many famous firsts associated with the X series: breaking the sound barriers, testing new materials, swing wings, high altitude flight. The X-14 itself was the first vectored thrust aircraft. In addition, there have been thousands of less famous firsts associated with technical advances, control systems and avionics. Much of what is known about flight today, and affects the planes of today and will affect those of tomorrow, rests on the results obtained by planes in the X series. It even seems likely that the X-14 may have been the first aircraft to have a pink circle for landing and takeoff. The X-14's flight test program started on the 17th of February 1957, and it completed the evaluation series for Bell in 1959. The Air Force then taking the plane over for an extended series of further general Vtol testing and pilot familiarization. Extended seems an inadequate word, actually, as the plane was to continue to be used by the Air Force and NASA until the 29th of May 1981. It was that day damaged in an accident and was written off as no longer airworthy. Today, fittingly for such a productive and successful little pioneer, it's preserved in a museum. Work on various schemes continued all over the world. In Germany, the Dornier 31 was a combination of lift jet and vectored thrust configurations. The Lockheed company invested a lot of its energy in augmented jet lift, in yet another method of heaving a plane straight up. Here, the theory stated that introducing jet thrust into a chamber of air would create additional lift from the engine's power by the rush of air into the chamber. And this was undoubtedly true, as it had been repeatedly shown to occur in test installations. However, in working the system into an aeroplane, the weight penalties of the installation went a long way to cancelling out the augmented thrust of the power plant, and Lockheed's Hummingbird was not a raging success, being later rebuilt with dedicated lift engines to test a completely different configuration. The use of lift-only jets by Lockheed and Dornier followed what seemed to be the emerging dominant pattern, using a number of small jets which only worked when the plane was in hover. The main engines were much larger power plants which operated in all phases of flight. The weight penalties of this are obvious, but they would be partially compensated for. A plane that had only its main power plant to obtain lift would need an extravagantly big engine, which would, in normal flight, never be called upon to deliver much of its available power. Of course, what happened to change the status quo was a breakthrough engine, developed by the Bristol company in England, the Pegasus. Around this engine, the Hawker company were able to develop their P1127, forerunner of the Kestrel and then the Harrier. The 1127 was a major step forward, an emphatic proof of the thrust vectoring approach, and drew extensively on the data obtained in the X-14 program. It was designed around the new engine, but for once, this did not place too unreasonable a set of demands upon the plane's shape or capability. The creation of a new engine is an expensive business, and to create a new engine for one application places a huge research and development load onto only one customer. And in the case of the P1127 and its basic development into the Kestrel, a lot of cost went into producing only a handful of aeroplanes. When the Kestrel project was completed, a lot of time and effort was put into design of a supersonic version, the P1154, and this almost caused the abandonment of the whole area of research by the company due to the huge bills involved and the lack of UK government support. Eventually, the plane that did emerge from Hawker's was a subsonic fighter, and initially there was little to no enthusiasm from the fighter pilots, who preferred to be at the controls of something that went considerably faster, preferably with as much glamour as possible. Today, the Harrier has come a long way, and the new AV-8B model incorporates a large number of advances and improvements. Though still subsonic, it now has doubled load capacity and range. The Harrier's successful use in combat and the successful development of tactics for its pilots have combined to underline that it is one of today's most potent and dangerous fighting machines, and it has been adopted for various uses. The McDonnell Douglas company has been involved in the project, together with British Aerospace, and the two companies have cooperatively developed the Harrier's capability and refined its airframe to ensure that it remains the most capable vertical takeoff plane in the world, at least for the moment. Who knows what'll be next, or what method it'll use. In 1971, the United States Air Force Tactical Air Command issued a specification for a short takeoff and landing advanced medium transport. This was intended as a replacement for the C-130 Hercules. The entries from McDonnell Douglas and Boeing were adjudged the best of those submitted, and the two companies were asked to proceed with prototypes. The McDonnell plane, the YC-14, drew heavily on the company's experience with licensed production of the Vertijet 941 deflected thrust transport. And the new plane was a logical extension of the 941 concept, replacing that plane's propellers with jet engines. The fuselage internal dimensions had been laid out in the specification. These resulted in a fat 120-foot fuselage with a DC-10 nose and a loading ramp under the upswept tail. The tail surfaces consisted of a tall fin carrying the horizontal stabilizer high up, away from the jet exhausts. The tail surfaces were of a large area to enhance slow speed control. At the wing's trailing edge were double slotted deflection flaps to direct the engine's thrust downward. The four engines were fitted with mixers to bring outside air to mix with the exhaust to cool it, but the deflection flaps still had to be made of titanium to cope with the heat. Two prototype YC-15s were built, and the first flight took place on the 28th of August 1975. Performance included speeds up to 518 miles per hour and payload up to 78,000 pounds. The relatively straightforward approach the plane took, with its huge mechanical intervention from the deflection flaps, based as it was on established technology, proved effective in giving the plane good results in the primary design aim, short takeoff and landing. And after a competition with the Boeing plane in fly-offs during 1976 and 1977, the YC-15 was declared the winner. However, this proved to be a hollow victory, as funding cuts saw the whole program cancelled in favour of the much more economic purchase of more of Lockheed's venerable Hercules. The Boeing entry, the YC-14, was an extremely different aircraft, though it too relied upon the deflection of the engine's thrust to obtain immediate lift, as well as the lift provided by the air on top of the wing. However, where the McDonnell plane directed its engines under the wing and then trapped them with a huge lowering air dam to deflect them downward, the Boeing had its engines placed to blow back over the top of the wing. There, the airflow was caught and deflected by the flaps which, when lowered, formed a smooth curve that relied upon the Coanda effect to divert the airflow. Wing lift was enhanced by full-span leading-edge flaps and by blowing compressed air from holes in the leading edge to obtain boundary layer control. spoilers were used to supplement the ailerons in low-speed roll control and to control the sink rate on landing approach. Thrust reversal was upward, which reduced the tendency to raise a dust cloud on unprepared landing strips, and enhanced braking by pushing the plane onto the ground. Two YC-14s were built, and the first flight was made on the 9th of August 1976. The plane demonstrated the ability to take off in 600 feet and land in 400, and it exhibited several other notable features, not the least of which was its quietness, a concept not usually associated with Vtol and STOL aircraft, where the engines are often screaming at full thrust in takeoff. The YC-14s operated from dirt fields and passed a range of other tests in the competition with the McDonnell plane. But despite its sophistication and success, it was not chosen as the winner of the competition. That the McDonnell plane was abandoned as well is probably not of much consolation to the Boeing team who drew up the 14's plans. In parallel to the numerous attempts to get a plane to act like a helicopter, there has been a drive to squeeze the last drop of potential out of the helicopter, and given that there's an absolute limit to how much use a rotor can be after it's got you into the air and you want to travel fast, the drive has been to add forward propelling engines to basic chopper shapes and let the rotors become essentially huge centers of drag. These are called compound helicopters. Howard Hughes built this huge compound helicopter, complete with engines on the tips of the huge rotor to drive it. Over the years, there have been a lot of variations on the theme, with or without wings, and an advance of over 50% has been made in the attainable speed. Mind you, there's no helicopter today that can fly as fast as the piston-engined fighters of the late 40s, let alone even look at what today's fighters can get up to when they're in a hurry. One of the obvious things to do is to put the rotors away when you're not using them. But this is not as easy as it sounds, and although several designs which incorporate stowing the rotors after takeoff have been developed, none have been successfully built. The other point about this is, of course, that once you've stowed the rotor away, your plane is just a plane until you take them out again. Whereas the developed and working technology of the Harrier, for example, allows chopper-like behavior at all times. Today's advanced helicopters have come a long way, and refinements continue to appear. But the limits on rotary-winged aircraft appear set to stay with us, and the future will probably see the two schools of vertical flight, choppers and Vtol planes, go on in coexistence, performing their respective roles. If you make a list of the elements you'd expect to find in an aeroplane, things like wings, tail, fuselage, you'll find that at some stage of aviation's history, some designer has done away with each of them. Some makes of aircraft have not had wheels, others have lacked fuselage and tail. The variety of shapes that have appeared at one time or another as aeroplanes is staggering. Yet, for each of them, there was a design idea that logically directed the outcome. Admittedly, some of the premises on which various shapes were based were either wrong or simply perverse, and some indeed look, if not insane, then certainly bizarre. We have our conception of what looks normal in an aeroplane. Yet, today's conception bears little to no relation to the first flying machines, and probably will bear only limited similarity to the leading edge of future aircraft design. It is, however, also true to observe that designers often pursue ideas that are ahead of their time, and that there are many instances, like the flying wing, where one era's designs had to await another era's technology or need to be proceeded with. When aviation began, it was not so much a matter of questionable data. There was no real understanding of what made flight possible. There were some ideas available that observably worked, but the essence of how they worked would not in fact be answered for many years. Hence, much common sense was wasted in following assumptions that were based on wrong interpretations of why some flying machines did work. In today's sense, there was no scientific basis to the avenues explored by designers. They tended to follow engineering ideas and mechanical advances, operating on a combination of intuition and experience that often led them astray, sometimes fatally. Quite often, their results looked downright comic to our eyes, though presumably, at the time, the designs that worked looked no less unlikely than those that didn't. By the 1940s, the variety of shapes considered were, in the main, based around configurations that we would recognize clearly as capable of flight, although still there was a certain amount of hopeful supposition about some elements. Here, Alexander Savesky, who founded what was to become the Republic Corporation, shows a model of his pet project for a long-range passenger seaplane. With its huge retractable pontoons and accommodation within the wings, the plane displays an attachment to past certainties, harking back to the flying boats. But it also exhibits quite modern considerations of drag, and one suspects, had it been built, it would have been fairly successful in meeting its design objectives. At the time, it represented the informed view of an aviation expert on what the future of the aeroplane would be. Today's designer looks to the future with the aid of sound scientific information and the huge capability of computers to study and assess his propositions. The shapes he looks at in his considerations of future demand can be extensively tested without being built, and those that will be built will have already been refined to extreme tolerances, with little to no uncertainty about their ability to perform. The restrictions he has to conform to relate to the complexity of the aeroplane and the cost of its construction.